Precalculus, lesson 13.4. This is probability of compound events. So we get to see what happens and how you calculate stuff when there are multiple events that you are considering simultaneously. All right? So 13.4, probability of compound events. And this can take different flavors. So, like a lot of probability stuff, what we do is we look at the different categories that can come up, and we look at some examples of scenarios that meet or that fit inside of whatever type or whatever category we're looking at. And that's just a representative sample. And so again, this goes back to the easy part of this kind of math is that the math itself, like the calculations, are not very involved. But the difficulty can be just the analyzing and determining, okay, wait a second, what is the scenario that I'm dealing with, and how should I go about calculating that? All right. So first we look at probability of two independent events. That's our first category here. Probability, I'm just going to do prob of two independent events. So what do independent events look like? They are events where the outcome of one does not affect the probability of the outcome of the other one. So for example, you roll a die, like a number cube kind of die. You roll a die and you see what you roll. And then you roll a die again. Did the outcome of the first roll affect in any way the options or the choices for what the outcome of the second roll will be? No. Those are independent events. Flip a coin 3 times. Each time it's an independent event. Draw a card out of a deck of cards, put it back, and then draw another card. Now, the putting it back makes the second draw independent. If you drew a card out of a deck and then you go to draw a second card without putting the first one back, that is no longer independent because your first draw affects the probability of the second one. All right, so stuff like that. So let's see. So independent events. So what we could say is the events, the outcome, maybe I'll say the outcome of one event does not affect the probability of the second event. Okay? And the kind of formula that we have here is P of A and B. Sorry, that should be a capital A. P of A and B is equal to P of A times P of B. So you just multiply the probabilities of however many different events you're looking at. So one example here could be like someone shoots, I'll say someone has an 80% free throw percentage. In basketball. Find, and I'll put it like this, P of make 3 consecutive free throws. Now, there's stuff that is kind of technically going on here that would not make this independent. For example, if the person makes the first one, that probably means they're a little better locked in and they have a good sense of their form being right and things like that. And so you could argue that, well, these are not truly independent events, but for the sake of the example, let's just work with this. Okay, so if each one is 80%, we want to find making three in a row. So then we would have P of three in a row is just going to be that 80%, or I'll say 0.8 to the third, right? Because it'd be zero point 0.8 times zero point 0.8 times zero point 0.8. And so what do we get here? 0.8 cubed is, as a fraction, I'll just do it as that is 0.512. So a 51.2% chance that this person has of making all three in a row, or 51.2%. Okay? One more example like this, then we'll move on to the next kind of thing. Let's do from the textbook number 17. Textbook number 17 says the probability of randomly selecting 2 oranges from a bowl of 5 oranges and 4 tangerines if the first selection is replaced. So you pull one out, see what it is. It's an orange, put it back, and then you draw another orange. So here's what we have. That would be with replacement, is how that is often referred to. So we have 5 oranges and 4 tangerines. So 5 oranges and 4 tangerines in a bowl. And let's find P of 2 oranges with replacement. All right. P of 2 oranges. I'll just go 2 oranges. No, I really need to say with replacement. With replacement. So what's the probability that you pull an orange out of the bowl? It's 5/9. You put it back. Now find the probability that you pull an orange again. Well, it's another 5/9. So what do we get? 25th, 25, 81st. That would be our answer there. I guess I could have boxed my answer here. All right, so that is independent events. Well, what if they are dependent? The math just changes slightly. It's more just like we need to be a little bit more careful with how we analyze it. So dependent events. And just like the explanation we had up here, I guess I should have said prob of 2. Let me go ahead and move this down a little bit. And then we'll say prob of 2 dependent events. So dependent events, how did I word that up there? Okay, yeah. The outcome of the first event does affect the probability of the second event. And here's our formula. So P of A and B. So we're still finding the probability that both happen. But now what we have is we call it like this. or we say it like this, P of A times P of B following A. That will make a lot more sense in just a moment, if that doesn't make sense yet. Let's do an example. Let's do number 27 from the textbook. Number 27 reads like this. So first it's, oh, hold on a second. I'm looking at the wrong thing. Wrong page. Not number 27. We're not to that yet. Number 5. Number 5. So, I mean, the first part of number 5 is determine if it's independent or dependent. Given the context, you can obviously tell this is dependent. So here's what we have. The probability of randomly selecting 2 navy socks from a drawer that contains 6 black and 4 navy socks. So we'll say drawer has 6 black CK and 4 navy socks. Find P of 2 black. Right? No, 2 navy. 2 navy. Without replacement. But it's not needed to say without replacement. It's more of if you are replacing it, it's more important to say that that's what's going on. If not, it's a little bit more assumed that there's no replacement. So you can look at this 2 different ways. 2 different ways. Let's say like 2 approaches. The first one is to view it as 2 consecutive events. So viewing it like this, it would be P of 2 navy is, well, first, what's the probability that out of the 10 socks, that the first one that you grab is navy? Well, there are a total of 4 navy socks out of a total of 10 in the drawer. So 4/10 would be the probability that the first sock you grab is navy. Now, assuming that the first sock you grabbed was navy, what is the probability now that the second sock you grab is also navy? Well, now that we've taken one of the navy socks out of the drawer, there are now 3 navy socks out of a total of 9 left in the drawer. And so multiply these together, you get 12 out of 90, which reduces, let's see, to 6/50ths, so then to 3/25ths. So 3/25ths. Okay? That's viewing it as 2 consecutive events. You analyze the probability of the first one. That would be P of A up here. And then the P of B following A is, we assume that a navy sock has already been taken out of the drawer. Now what is the probability of drawing a navy sock out of what's left? Okay? Now if you wish, you can also view this as drawing, draw a combination of 2 navy socks. So rather than viewing it as 2 distinct events where one followed the other, you can also view it as one event that involves a group of items, and in particular a combination of items. So here we could calculate it as P of 2 Navy is, well, how many different groups of 2 Navy socks can we form out of the 4 Navy socks that are there? Well, that's combinations of 4 Navy socks taken 2 at a time. And then the total number of possible outcomes is the total number of different groups of 2 that we can form out of all 10. So a combination of 10 items taken 2 at a time. So that's going to be 4 factorial over 2 factorial, 2 factorial over 10 factorial over 8 factorial, 2 factorial. And the combination of 4 taken 2 at a time is 6. And the combinations of 10 taken 2 at a time, if our math is right, it should be, wait, did I do the earlier one right? Oh, 90. Hold on a second. Back up here. 10 times 9 is 90. But when you cut that in half, you get 6/45ths, not 6/50ths. So then so 6/45ths. And that does go into, so 6 can divide by 3, 45 can divide by 3. So yeah, 2/15ths. My apologies if you were watching for a little while and were like, earlier, and were like, no, you didn't reduce that right. The detailed part of my, I don't know. I feel like there are kind of two different math brains. There's the computational kind of math brain and the conceptual kind of math brain. And I'm much stronger at the conceptual side of things. I can do the computational stuff fairly well, but the more that I'm focused on the concept and communicating the concept, the more prone I am to make a mistake with the computational side of things. Anyway, the combination of 10 taken 2 at a time was 45, and that reduces also to 2/15ths. So there you go. Take your pick. Now you might be like, the first approach seemed way easier. And for a problem like this, yes, that's true. But depending on the context, it might be a bit cumbersome or a bit difficult to view it as two consecutive distinct events, and viewing it as combination can be a lot more efficient or easy. All right, so that is, what are we doing with there? Probability of 2 dependent events. The next topic we have for this lesson is probability of mutually exclusive events. So we'll go prob of 2 mutually exclusive events. So what do we mean by that? We mean that it is impossible to satisfy the criteria of both probabilities or of both events at the same time. An example would be like rolling a 2 and a 5 on a number cube. Or like drawing a heart and a club out of a deck of cards. Drawing a 5 and a jack out of a deck of cards. No 5s are jacks and no jacks are 5s. No 2s are 6s and no 6s are 2s, kind of a thing. And so they are mutually exclusive. You cannot satisfy both criteria at the same time. And so what this looks like is P of A or B is P of A plus P of B. So earlier we were multiplying our probabilities. And when you multiply fractions that are less than 1, your result is smaller than either of the fractions individually. And so, the scenarios we were dealing with before, we ended up with probabilities that were lower than just any of the individual probabilities happening by themselves. Here, we are adding fractions, and when you add fractions, the value that you get is bigger than what you started with, and that makes sense. If you're saying, I mean, if we go with a really basic example, it'd be like, what's the probability that you win or lose the game? What's the probability that you make or miss the free throw? Well, if you're going something like making or missing the free throw, and if a person shoots 80%, the probability that they make it is 80%. The probability that they miss it is 20%. Add the two, there's a 100% chance that you will make or miss this free throw. All right, kind of a thing. But that, well, yeah, I'll leave it at that. All right. Well, speaking of, well, no, let's do number 7 as an example. So, example number 7. Sorry, I didn't give a little written explanation of what would mean by mutually exclusive events. Hopefully, just my verbal will work. The probability of choosing a penny or a dime from 4 pennies, 3 nickels, and 6 dimes. So we have 4 pennies, 3 nickels, and 6 dimes. And we want to find P of 1 penny or 1 dime. 1 penny or 1 dime. Okay. Well, that's just going to be the probability that you pull a penny. There are 4 pennies out of a total of, say, 4, 5, 7, 13, right? So you have a 4/13 chance of drawing a penny, and then you have a dime, 6/13 chance of drawing a dime. So therefore, the probability that you pull a penny or a dime is 10/13. Now you can also kind of look at it as, how many pennies and dimes do I have? Oh, I have 4 pennies and 6 dimes, so I have a total of 10 pennies and dimes out of how many total items? 13 total items. Again, you get 10/13. Okay? Let's build on the free throw thing, but look at how we have to be careful about accounting for everything that's going on. So let's find the probability. Let's find, we'll say again, 80% free throw percentage. Free throw percentage. And let's find P of make at least 1 of 2 attempts. Now here's what it can be easy to do. Let's just say that instead of finding the probability of making at least 1, that we found instead the probability that we're asked to find, what's the probability that the person will make that the person takes 2 free throws and they make 1 of them. And it's tempted to be like, oh, well, there's an 80% chance that the person makes the first free throw. And then there's an 80% chance that the person makes the second free throw. Therefore, there's a 160% chance that they make either the first or the second. That shouldn't seem right, because the probability of 100% is certain. Probability of anything over 1 or over 100% is nonsense. So what we have to do is we have to look at it like this. If the person makes just the first free throw, What does that mean they do on the second attempt? Well, if they make just the first one, then they miss the second one. And so we have to include the probability that they miss the second one. Okay? So it would end up looking like this. So let's say P of make at least one would equal, I'm going to do some words here so you can see what's going on. Make the first and be kind of like this. They could make the first and miss the second, or the person could miss the first and make the second, or they could make both. Let me scoot that up a little bit. Or they could make both. That's what would satisfy the criteria of making at least one of them. They make the first one, but not the second. They make the second, but not the first, or they make both. So then what that ends up looking like with the math is making the first, but missing the second would be, oops, 0.8, a 0.8 chance of making the first, and so we're multiplying because they're independent events, a 0.2% chance. Well, we're multiplying because they're independent events that we're looking at happening where we want both outcomes to happen. Make the first and miss the second. Or the person misses the first and makes the second, or the person makes the first and makes the second. And so multiply all these out, 0.8 times 0.2, oops, 0.8 times 0.2 plus 0.2 times 0.8 plus 0.8 times 0.8, and we get 96% chance. Guess what the remaining 4% is? The remaining 4% is that they miss both of them. And that would be the other way of doing it. It would be to calculate the percentage chance that the person misses both, which would be 0.2 times 0.2 or 0.04. And then the remainder is the possibility that they make one or the second or both. And so if you did 100% minus the 4% chance that they miss both, then you would also get this 96%. Okay? So that is probability of mutually exclusive events. Next and finally, last topic from this lesson is prob of two inclusive events. And what we mean by that is, I think a Venn diagram can be helpful. Well, I'll just say this: there's overlap between the two probabilities. There is overlap between the two probabilities. So that would be like this. We do a little Venn diagram kind of a thing. And we'll say that this is P of A. And then this, sorry, these circles are really bad, is P of B, and there's an overlap. Okay? So let's just say we make it like P of A is drawing a red card out of a deck. Draw red card out of a deck. A 52 eraser. There we go. Out of a 52 card deck. And let's say P of B is draw a face card. So the overlap here is the face cards that are red, okay, or the red cards that are face cards, all right? So what we have to do is we have to say P of A or B is P of A plus P of B. Now watch what happens if we do that. Let's just say P of A is yellow. And let's say P of B is blue. Now when we add these, what have we done but this red section, we have counted it twice. Do you see that? Because we counted that red section once with yellow, and then we're counting it again with blue, and we can only count it once because otherwise our percentage is messed up. So what we need to do is we need to subtract the overlap. And so we need to subtract P of, I'm going to say A intersection B. That would be this. And that symbol means intersection. In other words, it's the overlap. All right, well, let's just go ahead and do this example. So we'll start with that, and then we'll do one from the text. Find P of red or face card. Well, the red card's as half of the deck, or we could say 26 out of 52, or 1/2. The face cards, well, let's see. Face cards are jacks, queens, and kings. So there's a jack, queen, king for each of the 4 suits. So 4 times 3, so there's a total of 12. 12 out of the 52 cards are face cards. But the Jack, Queen, King of Hearts and the Jack, Queen, King of Diamonds, we already counted when we counted all the red cards. So we need to subtract those out. So we need to subtract out the 6 cards that are red face cards. And put all those together. And what are we actually doing? 26 plus 6. So 32. 32 out of 52, which reduces to 8/13. So you have an 8 out of 13 chance of drawing either a red card or a face card out of the deck. So 8/13, what percentage is that? That is approximately 62%. Which makes sense that if the red cards are half of the deck and you're adding to that some additional face cards, that it would be greater than 50%. Okay, one more example. Sorry, this lesson is taking a little while. This is just the nature of this lesson. The final example I have here is number 27. Let's see what that is. I might not feel like doing it if it's... Oh, number 27 is exactly this. That is a red or face card. I must have had that in the back of my mind when I decided to do this as an example. So there we go. that is this lesson. As always, let me know if you have questions, and I hope it goes well.